Hi everyone. So our next topic is wave reflections. So that we are going to study in the next lecture. In this lecture we are going to study boundary conditions because these boundary conditions will be used in our next lecture. So that's why we are going to study it. So do not take this topic as a prerequisite. Why is that so? Because this is mentioned in your syllabus. In your syllabus they have specifically mentioned this particular topic, that boundary condition EC guys should study. So you can expect some question from this topic only. So do not take this as a prerequisite. Study it thoroughly, study it completely and understand all the concept. So we are going to solve a lot of problems in that, and then it will be all clear to you. In the next lecture we will again move to EM wave. So this topic is not related to EM wave at all. This topic is related to electrostat and magnostat. So this has nothing to do with EM wave. So in this particular lecture we are not going to discuss EM wave. In this particular lecture we are going to study boundary condition. But before going into boundary condition, we need to study vector algebra. So first let's revisit our vector algebra. So just you need to solve some question. The concept has been already taught in vector algebra itself. Just I am asking you some questions. Okay. So basics of vector algebra we will see. So this is a plane, x equals to 0 plane is there, and then there is a vector field. This vector field is 3x cap plus 4ay plus 5az cap. So this is the vector field. Now what you need to find? You need to find the vector component of A, some component of A which is parallel to this plane and perpendicular to this plane. Is that clear to you? This is your xyz coordinate. Where will be your x equals to 0 plane? This we have already studied, like a lot of times we have studied. Where will be my x equals to 0 plane? This will be my x equals to 0 plane. This is my x equals to 0 plane. Now what will be my perpendicular component? What will be my perpendicular component to this plane? That will be in x direction. So that will be ax cap. And what will be my tangential component? Tangential, or you can say parallel component. So on this particular plane, what all component will be there? Y and z. Y cap and az cap. So our first task is first to find the perpendicular of this plane. So our plane is x equals to 0. Our plane equation is x equals to 0. So from there what I will do, I will make a scalar field function that is x minus 0, and then I will calculate the gradient. And if I calculate the gradient, what do I get? Calculating the gradient, what do I get? I get the perpendicular vector. So what is my perpendicular vector? Perpendicular to the plane. What will be the gradient of this? That is ax cap. So my perpendicular component is ax cap. Now what do I need to find? I need to find the component of A which is perpendicular. So perpendicular component. Perpendicular component. Can I write it down in this manner? A perpendicular. So what do I need to find? The component which is in the direction of ax cap. The component which is in the direction of ax cap. What is that? 3x cap. So this is the x equals to 0 plane. Now this A is having three components: 3ax cap, 4ay and 5az. 3ax, 4ay and 5az. Combining this you get 3x cap plus 4ay cap plus 5az cap. So these are its three direction, right? So whatever the component is there in ax cap direction, that is known as perpendicular component. So what is the answer? 3ax cap. Now this we solved using intuition, but how you would have solved it mathematically? If you need to find perpendicular component of A, then first you need to find what is the perpendicular component of this plane. Like what is the perpendicular unit vector of this plane? That is ax cap. So now you need to find the component of vector A in ax cap direction, and the direction is ax cap. Is that clear to you? Do you remember this thing? Component of vector A on B, that is the scalar component, and if I need to associate the direction as well, then I will put B cap. So do not ignore this thing. This is how you find it mathematically, because this was a very simple equation of plane. This was very straightforward, that you know that ax cap will be the perpendicular component, ax cap will be the perpendicular component, so answer is 3ax cap. But if some different plane is coming, like 3x cap plus 4ay plus 5z is equals to 1, if that plane is coming, then what you will do? First you will find the perpendicular unit vector. First I will find the perpendicular unit vector, then I will take the component of A in the direction of perpendicular unit vector. So I am taking the component of A in ax cap direction, and I need to associate the direction as well. So if I find this thing, so what I need to do? A dot ax cap. a dot ax cap, that will be 3, right? 3, and then direction is 3x. So this is my perpendicular component. So this I can say method 1, like this was simple your intuition, and this is the mathematical way. So mathematical way is also important. And what will be your parallel component? What will be your parallel component? Parallel component will be y component and z component together. So 4ay plus 5az. 4ay plus 5az. This is the method 1. Now what could be the method 2? So one thing I know is that any vector a can be written in two parts: parallel vector and perpendicular vector. Basically, along any plane, your vector a along any plane will have some perpendicular component and will have some tangential component. What I am saying, your vector a along any plane will have some perpendicular component and will have some tangential component, right? So this a vector can be written as perpendicular plus tangential, or you can say parallel. Both are same thing, okay? Parallel, or you can say tangential. So I already know this thing, which is 3x cap, and I already know I already know the a vector. A vector is 3ax cap plus 4ay cap plus 5az cap. A parallel I need to find, and a perpendicular I already know, which is 3ax cap. So from here, what I am getting, that is, so this was just a revision example which you could have already solved very easily, right? You do not need to do all these mathematical calculation. You could have solved it very easily, but in the examination this question will not come. In the examination this question will come up. So how will you solve these kind of problem? So this is the equation of plane now. Now your plane is something like this. This is your plane. I don't know how this plane would look like, but I know the equation of that particular plane. And then I have a vector A. Now you need to find perpendicular and parallel component. So now we need to use mathematics. So what will be the perpendicular unit vector? First I need to find perpendicular unit vector. So what that would be? What I need to do? I need to calculate the gradient. So I will make a scalar field function which is 3x, 2x plus 3y plus 4z minus 12. Now I need to find the unit vector. This an cap I need to find. So my an cap would be 2ax cap plus 3ay cap plus 4az cap divided by its magnitude. So that would be 4 plus 9 plus 16 under root 29. That would be under root 29. So this is my an cap. Now I need to find the perpendicular component. How would I find the perpendicular component of A? A can be written as perpendicular component and parallel component. So what will be your perpendicular component? Perpendicular component to this plane. So that will be in the direction of an cap, right? If I need to find the perpendicular component, that means that will be in the direction of an cap. So what I will write? A perpendicular will be equals to a vector dot an cap, and the direction will also be an cap. Is that clear to you? So that's why we solved this question. Here the perpendicular component should be in the direction of ax cap. So what did we do? A dot ax cap, and this is the direction. Same thing we are doing here. A dot an cap, and this is the direction. So now I am gonna do a dot an cap. So what will be my perpendicular vector? Perpendicular vector a dot an cap. 5 into 2, 10. Basically, let me write 5, 6, 7. So 5 ax cap. In the examination, you are not going to write these steps, but since I am explaining, that's why I am writing it. Plus 7 az cap. Dot with 2, 3, 4. 2, 3, 4. 2 ax cap plus 3 ay cap plus 4 az cap divided by under root 29. Now this is just the component, this is just the magnitude. Now I need to associate the direction as well. The direction will be this: 2 ax cap plus 3 ay cap plus 4 az cap divided by under root 29. Okay. So 10 plus 18 plus 28. Again 10 plus 18 plus 28 divided by under root 29. So this is the magnitude and this is the direction, which is 2ax cap plus 3ay cap plus 4az cap divided by under root 29. So under root 29 and root 29, this will be 29 only. So 28, that will be 56, right? Tan 18, 28, 26. 26 plus 26 is 56, sorry, divided by 29. This is 56 under root 29 under root 29. So 56 divided by 29. 2ax cap plus 3ay cap plus 4az cap. Let me solve it. Using the calculator, I will solve it. So you can also do the same thing. I will pause the video and solve it, then write down the final answer. Okay. Yeah. So this is the perpendicular component we are getting. Okay. So this is our perpendicular component. Just by doing the calculation, this is what you are getting. So this is your perpendicular component. Now what do you know? That your A is equals to the parallel component and the perpendicular component. So A already you know, 5ax cap plus 6ay cap plus 7az cap. Then it would be parallel component plus perpendicular component will be 3.86ax cap plus 5.79 ay cap plus 7.72 az cap. What will be your parallel component? So 5 minus 3.86. 5 minus 3.86. It's not that tough. Still I am doing with calculator. 5 minus 3.86. 1.14. Should be very easy. I already knew it would be 1.14, but still just be happy with the calculator. This will be 0.21. 0.21 ay cap. And this will be minus 0.72 az cap. Right? 5 1.14, 6 minus 0.21, and this is 0.72 az cap. There you go. This is your vector parallel component. So parallel component and perpendicular component you must have got. Okay, so these are the parallel and perpendicular components. So this was a very basic of vector algebra which will be used in boundary condition. So there we need to find the perpendicular and parallel component of electric field or magnetic field. But here we just assumed a simple vector, right? Let's move to some important points regarding the conductor. So related to conductor, we are going to study some important point. So first point is electric field inside the conductor is 0. So let's just say it is some electric field. Some electric field is there. These are the lines of some electric field. So what do? I place a conductor in between. I placed a conductor in between. So what will happen to this electric field? So in the conductor, you always know that there will be some electron and positive. Electron and proton will be bounded. In any conductor, there will be electron and proton will be bounded, right? Now, since there is an electric field, so this electric field will put some force on electron in the opposite direction. If you remember, this was our electric field. So electron will feel the force in the opposite direction and positive charge will feel the force in the same direction. So now this electric field will put the force on electron in the opposite direction. So electron will be coming this side and proton will be coming this side. That means positive charge will be coming this side. Firstly, negative and positive charge was bounded. These were not free. They were bounded. Just as the electric field came, what did it do? What did the electric field do? That it put the force on electron in the opposite direction. It put the force on proton in the same direction. So this is how this will be your electron. This will be your negative charge and this will be your positive charge. Now, because of these charges, this is your negative charge, this is your positive charge. This is your negative charge, this is your positive charge. Because of these charges, there will be one electric field generated, right? Initially, there was the electric field. This was external electric field. This electric field was external. This was coming from somewhere. Now, because of this electric field, the positive and negative charges got separated. Now, because of this positive and negative charges, there will be one electric field which will be in opposite direction, right? Electric field will always be from positive to negative charge because this is positive, this is negative. So, from positive charge, electric field lines go out and in negative charge, electric field lines come in. So, from positive to negative, there will be electric field generated. So, this electric field, this was your external electric field, E external, I am calling it E external. So, this electric field will be in the opposite direction to an external electric field. This was having this direction. Because of the charge separation, there is another electric field which has been generated, which is opposite, in the opposite direction. So now this electric field, I am calling it E internal. Now this E internal electric field is reducing this external electric field. This internal electric field is reducing this external electric field. So now the magnitude of this field will go down. Now let us say the magnitude has been gone down. Initial magnitude was this. This was your E external. Now the magnitude has gone down. Now again there is some electric field present. Again there is some electric field present. So again electron and proton will be separated. This is your electron, this is your proton. Again electron and proton are separated. So again there will be another E internal field. So again it will reduce the amplitude. So till what point it will reduce the external electric field? Until it becomes 0. Is that clear to you? Again let's restart. There was electric field. So in the conductor there was electron and proton. They were bounded. But since the electric field came, they got separated. If they got separated, so proton was feeling the force in the same direction of electric field, electron was feeling the force in the opposite direction. So this is how they got separated. Since they are separated now, so because of that, there will be some internal electric field generated. So there will be one internal electric field will be generated, that is from positive to negative, right? So that is the electric field. So this is your external electric field, this is your internal electric field. Both are cancelling each other. So let's just say the amplitude is decreased to this much amount. That means electric field has been reduced. But since some electric field is still present, if electric field is present, again electron and positive charge will be separated. If electron and positive charge are separated, then again in the opposite direction, again there will be electric field. So again it will be reduced. So till what point it will keep on reducing? Until it becomes 0. So inside the conductor there will be no electric field. Is that clear to you? So this is the explanation, which is not important for your examination. But if you want to remember that why that is happening, that's why I have given this explanation. Not important for your examination. Okay. So I will just remove it off. Just put the conductor. So some electric field lines are going. Some electric field lines were some electric field lines were going, and in between I placed a conductor. And once I place the conductor, so there will be no electric field lines within that. Okay. So this conductor will eat up all the electric field lines. Is that clear to you? So electric field inside the conductor is 0. These will be used in our boundary condition. That's why we are studying it. It will be used in our EM wave as well. And in EM wave, what did we study? If a wave travels, this is your air, this was your conductor. So if the wave in the air was this, but once it goes into inductor, it loses its amplitude and then becomes 0. Do you remember this? Because there will be some sigma. If there is some sigma, that means there will be some attenuation constant. So that means the wave will be attenuated and eventually it is going to be 0. So in the conductor, it will take very minute distance, like your skin depth will be very, very low. Your skin depth will be very, very low, and in a very minute distance, it will become 0. So inside the conductor, electric field will never be present. Is that clear to you? But whatever that minute distance is, like it will take some time, it will go for some distance. Based on that distance only, we study our EM wave inside the conductor. Okay, but eventually it will be becoming 0 only. So electric field inside the conductor will be 0. So this was our first point. Let's study the second point. Excess charge will always reside on the surface of conductor. What do I mean by that? So this was our conductor. This is a sphere. Okay, this is a sphere. This is not circle. This is a sphere. This is a sphere. Okay, this is not a circle. This is a sphere. So this is our sphere. Now I give some excess charge to it. I am giving plus Q charge to it. So what they are saying, it will always come on the surface, not inside the sphere. This is, I am having a sphere. I am having a sphere where it is, okay. Yeah, so this is my conductor. If I give the charge to this conductor, then this charge will be placed on the surface only. It will not go inside. This is what they are saying. So let's prove that why it is not going inside. Okay. So I am giving plus Q charge. Let's just say it goes inside. I am assuming that it is going inside. If it goes inside, then what happens? Let's check that out. So again, there are electrons and proton. Electron and proton are bounded. Now, in this whole circle, electron, proton was there. Electron, proton, electron, proton, electron, proton, electron, proton, and all were bounded to each other. So number of electrons and number of proton, both were equal, right? It was not charged. Rho v was 0. It was not charged. Number of electron and number of proton were equal. Both were closely bounded. Now you gave it excess charge. That means you applied some positive charge. Now what will happen? This electron will come. This electron will be attracted by this positive charge. So this will come. Again there will be another electron. This will come here. Again there will be another electron. This will come here. Then again there will be another electron which is bounded to proton. This will come here. So 4 electrons which are bounded to other protons, 4 electrons which are bounded to other positive charge, they has been attracted by these positive charge and have, what will happen is that this electron will travel here, it will neutralize it. This electron will travel here, it will neutralize this. This electron will travel here, it will neutralize. This electron will travel here, it will neutralize. So now what will be your revised condition? Your revised condition will be from here to here. What will be revised condition? So this charge is losing its electron. This charge has lost its electron. So now this is also free. This is also free. This guy is also free and this guy is also free. Again there will be some electron and proton. Electron, proton, electron, proton, electron, proton. So what will happen? This electron will be attracted by this positive charge. This electron will be attracted by this positive charge. Another some electron, proton will be there. That will be attracted by this positive charge. Another electron, proton will be there. So this will be attracted by this positive charge. So eventually what is happening is that you put the charge inside the conductor, but it is spreading out. Like attracted by this electron. So this is free now. This is free now. This is free now. This is free now. Now this will be attracted by some other electron. So this positive charge will be free. So eventually it will come on surface only. Are you getting this point? Inside I put, then electron neutralized it, some free proton. Then that proton will be neutralized by some other electron and then free proton. So this free charge will come out on the surface. So whenever I give the charge, that will stay on the surface only. That will not go inside. Okay. Is that clear to you? So eventually you need to remember the result. Like how it came, that is not important. How it came, that is not important. So what did I say? The excess charge will always go onto the surface. Here what did we say? The electric field inside is 0. Now the excess charge will go onto the surface. So this is the second point. So if someone asks you the reason in some interview, then you can say electron, proton. So if I give some excess charge, then this will be neutralized, then this is a free proton. Then again this will be neutralized, this is a free proton, then that will go onto the surface. That's it. Okay. Very simple, very straightforward. The third one, electric field lines are always normal to the charged conductor. So this is our conductor which is charged. This is our conductor which is charged. Now they are saying that electric field lines are always perpendicular. What do they mean by that is that this is how the electric field lines would be there. That here it will always make 90-degree angle. So let's prove it. So first what we are going to do, we are going to assume that electric field line is not perpendicular. What I am going to assume is that electric field line is not perpendicular. This is what I am assuming. That it is making some angle theta. With conductor it is making some angle theta. So this is my electric field line. So can I break it into two components? Yes. This will be your E cos theta, or I can write E parallel, I can write E tangential, I can write, or E parallel, whatever you call it, and this is my E perpendicular. E perpendicular. So what will happen now? Now this E tangential, or you can call it E parallel. This E tangential will be cancelled by what? Here there is electron, here there is proton. Because of this electric field, electron will feel the force in this direction. So electron will be present here and proton will feel the force in this direction. So proton will be present here, and because of that there will be another internal electric field generated. And because of this electric field, this component will cancel out. Only the perpendicular component will remain. That's it. Is that clear to you? On this surface only, because of this tangential component, or you can say because of this parallel component, because of this tangential component, there is another electric field generated which is in the opposite direction. So that is cancelling out this component, right? So tangential component will be cancelled. Only the perpendicular component will remain. This E was broken into tangential and perpendicular component. Since it was broken into tangential and perpendicular component, so we need to study about these tangential and perpendicular components. So tangential component will generate some electric field which is opposite to its direction. So that will cancel out both of the electric fields. So only the perpendicular component will remain. Is that clear to you? So if you give some charge, if you give some external charge, this is your charge conductor. This is how your charge conductor will look like, and the electric field will always be perpendicular. So this is how the electric field will look like. So these derivations are not important, but once you study the derivations, you feel good. I am not saying this is derivation actually. This is just a way of understanding the things. So now this electric field will always be perpendicular. Electric field will always be perpendicular. This doesn't look like perpendicular. So all these are 90-degree angle. Okay, and if it was negative charge, then this was your conductor, and let's just say if it was charged negatively, if I give some charge, that will come on the surface only, and if it was charged negatively, then what would have been the direction? Then the direction would have been something like this, because in the negative charge the electric field converges, and from the positive charge electric field diverges. So that point we have already studied. So it is converging. Electric field lines are converging. Okay, so from positive charge it will go out, and in negative charge it will converge, and always making an angle of 90-degree. So all these are 90-degree. Okay, so what is the summary? 3 points we need to study. Inside the conductor, zero electric field. When you give the charge, it will come on the surface, and the electric field lines from this particular charge will be always perpendicular. That's it. So what is the conclusion? This is the conclusion, that these were the electric field lines. If I place some conductor in between, so what will happen? These will be gone. And if I give some charge, so that will come on to the surface. Okay. One more point is there, that this surface will be equipotential surface. What do you mean by that? Equipotential surface. Okay. One more point is there. You can assume it as a fourth point. Equipotential surface. What do I mean by that? That means if I am giving this Q charge, so that charge will come equally distributed. Like if I give some ρs charge, ρs means this is my surface charge density. So that charge will be equally distributed. Now let us say this is some surface, and I pour some water. So it may happen that some water is, the density of water is more here, the density of water is less here. Like if I am pouring some water, so some more water will be here, less water will be there, right? But if I give the charge on this particular conductor, if I give the charge on conductor, then charge will be equally distributed on the whole surface of conductor. Like it will be equipotential surface. That means at all the points of this surface, the charge will be same. Is that clear to you? Okay, so that's why it is known as that conducting surface is equipotential surface. Is that clear? When I give the charge, it will be equally distributed on the complete surface. Okay. So this is the fourth point which you may remember. It will not be asked in your examination because these are the points of electrostat. But once we study boundary conditions, so there I will be using these points and will be solving some numerical. So in numerical problem solving, it can be used, and this can be asked, these numericals can be asked in your examination because this boundary condition has been mentioned in your syllabus. If it was not mentioned, then I would have taught this particular topic on a very surface level. But since it is mentioned, so that's why I need to teach it very deeply, like all the aspect of it I need to teach. So this we have studied about conductors, and we have studied some basic vector algebra. We haven't started studying our boundary condition till now. So now we will study about boundary condition. So I will take a break. You can also take a break. You can drink some water, and then we will start studying about boundary conditions. Okay. So let's start studying about boundary conditions. So we will study it for electric field as well. We will study it for magnetic field as well. So first let's study the boundary condition for electric field. So what do you mean by boundary? Okay. So forget about this diagram. Just look at me. So let's just say this is a boundary. You will understand the meaning of it. What do I mean by boundary? That this side of boundary is having some other medium, and this side of boundary is having some other medium. What do I mean by that? That on this side of the boundary, let's just say I am having some air, and at this side of boundary I am having some dielectric. It could be lossy dielectric, it could be lossless dielectric. So it will have its some sigma, epsilon and mu, and this will also have its own sigma, epsilon and mu. Are you getting this point? This is not actually present. Boundary is not actually present. here there was air, at this side there was air, at this side there was some dielectric. So there will be a separation in between. Now let's just say I am walking in air, and after some time I am going into dielectric. So there will be one boundary node which is separating air and dielectric. So that is known as boundary. So this is your boundary. So this side of boundary. So this side of boundary is your air and this side of boundary is your dielectric. So it could be any medium. It could be this side could be dielectric, this side would be conducting, this side could be conducting, this side would be dielectric, this side could be air, this side could be low/dielectric, low/dielectric. It could be anything. So I am writing it as medium 1 and this is your medium 2. So this medium 1 will have its own sigma, epsilon and mu, and this medium will have its own sigma, epsilon and mu. Okay. Now this is my boundary, right? This is my boundary. Now one electric field is traveling like this. Now this electric field is traveling in air. I am assuming this is my air and this is my dielectric. Okay, and in between there is a boundary. So one electric field is traveling. It is traveling in air. Then certainly it is struck to the boundary, and next part will be in the dielectric. It is traveling in air. Then it struck here, and the next part will be your dielectric. Is that clear to you? Traveling in air, then it is going into dielectric. So this is what I have made here. So this is traveling in medium 1. And then after this it is going into medium 2. Is that clear to you? So what will happen, like which component of electric field will change, that we need to see. It was traveling and then it is going to the other medium. Now we need to study about these components. So now this electric field will have its own tangential component and it will have its own perpendicular component. What do I mean by perpendicular? Perpendicular to the boundary. If I am saying tangential component, that means it is tangential to the boundary, and if I am saying it is perpendicular component, that means it is perpendicular to the tangential, perpendicular or normal. N stands for normal, okay, and T stands for tangential. So normal and tangential to what? To the boundary. So this is my tangential component, this is my perpendicular component, or you can say there will be perpendicular component of D as well, there will be tangential component of D as well. What is my E? E is electric field intensity, and what is my D? Electric flux density. Do you remember the name? E is your electric field intensity and D is your electric flux density. Same goes here. This will also have some perpendicular component and normal component. Sorry, this is your tangential, this is your normal. This was your tangential component, E tangential, but in the medium 2, and this is your E normal, but in the medium 2, or along with that it will have some D normal, but in the medium 2. So this was your tangential component, D tangential in the medium 2. Is that clear? Electric field was there. Here also there was electric field. This was having tangential component, normal component. This was also having tangential component and normal component. Now because of the boundary condition, so what your boundary condition says? So I am writing my boundary conditions here. So what does my boundary condition say? My boundary condition says that your tangential component of electric field will be equal, okay, and normal component of electric field density will have this relation, which is d2n minus d1n dot a12 is equals to rho s. What do I mean by that? Let me explain it. So these are the two statements which you need to remember, but let's understand the meaning of it. What they are saying, that this tangential component E1t will be equals to E2t. They are certainly vectors, right? They are certainly vectors. There is no doubt about that. They are vectors. So this tangential component E1t is equals to E2t. Now we are having the relation for perpendicular component of electric flux density. We are not having the relation for perpendicular component of electric field intensity. This is your electric field intensity. For perpendicular component or for normal component, you are having the relation in electric flux density. Okay, eventually you are going to remember it, but let's just see what does it mean. That d2n, this is your d2n, or you can say dn2. I should have written dn2. No, d2n only. this I have written wrong. D2n, D2 normal, D2 tangential, D2 normal. So D2n minus D1n dot A12. What do you mean by A12? A12 is the perpendicular component from medium 1 to medium 2. So basically from medium 1 to medium 2, this is your A12 cap. Let's just say this boundary was x equals to 0. Assuming this boundary was x equals to 0 and this medium was x less than 0 and this medium was x greater than 0. This was your boundary which is x equals to 0. This was your x less than 0, this was your x less than 0 and this was x greater than 0. Basically here you are having minus 2, minus 3, minus 4 like that, and here you are having 1, 2, 3, 4. So what will be your A12? From medium 1 to medium 2, from medium 1 to medium 2, a perpendicular vector. 1 to 2, a perpendicular vector. What that would be? Ax cap. Is that clear to you? Because this is your x equals to 0 plane. X equals to 0 plane. And what is the perpendicular component of x equals to 0 plane? Perpendicular component of x equals to 0 plane. What that would be? Ax cap. So whether it would be plus Ax cap or minus Ax cap, so that will be defined from 1 to 2. 1 to 2. That will be plus Ax cap, because I am going from x less than 0 to x greater than 0. That means the value of x is increasing. If the value of x is increasing, that means Ax cap. If I was going from 2 to 1, so the value of x is decreasing from x greater than 0 to you are going to x less than 0. So if it is decreasing, then it would have been minus Ax cap. But since it is increasing, so it would be Ax cap. So this is just the example I am telling you. Okay. So what is your A12? Is that clear to you? From medium 1 to medium 2, A12 perpendicular vector, perpendicular unit vector you should say. So this is your A12. So D2n minus D1n dot A12 is equals to rho s. What is your rho s? Rho s is the surface charge density. So on this surface, if there is some charge, basically this was your air, this was your dielectric. So let's just say I put some surface air, like this is the surface which is, this is your air and this is your dielectric. So this is the surface which is making it two medium. This is air, this is dielectric. So on this particular surface, if there is some charge present, so that is known as rho s, surface charge density. And it will have the unit of Coulomb per meter square. Okay, air, dielectric, in between there is some surface. So it has the unit of Coulomb per meter square. So on this boundary, if there is some charge present, so it will be equal to that. Is that clear to you? How will you remember this? So I will tell you the trick to remember this as well. So how will you remember? Do you remember Maxwell's equation? D dot ds is equals to rho v and E dot dl is equals to 0. Like it was different in case of time varying field, but let's just consider these equation for static field. Okay, and I am just telling you I am just telling you the way to remember these formula. So if I ask you to write down ds vector, what will you think? First thing will come into your mind is that you need to tell me about normal component. You need to tell me about perpendicular component. If we need to write down that ds vector, so how we will write down? Ds and the perpendicular component to the surface. So if I am thinking about perpendicular component, that means I need to think about d. Actually these have been derived from these formula only. Okay, but I am just telling you a way to remember, nothing else. Okay, in longer run you are going to remember it only. E1t is equals to E2t, D2n minus D1n dot A12 is equals to rho s. In longer run you will be able to remember it, there is no doubt about that. But for a short time, how will you remember? That if I am talking about a perpendicular component, d dot ds is equals to rho v. So if I am talking about perpendicular, or if I am talking about normal, that means I am talking about ds, and if I am talking about ds, so that will be associated with d. So for normal component you have the relation with d, and for tangential component you have the relation with e. Is that clear to you? For normal component you have the relation with d, for tangential component you have the relation with e. Now this is equals to 0, right? E dot dl is equals to 0. So if there is something which is equals to 0, E dot dl is equals to 0, So there will be very simple formula, like this will be equal only. E dot dl is equals to 0, that means E1t is equals to E2t, like very straightforward. But this is equals to some value. So if this is equals to some value, then there will be complex formula. This is just a way to remember, I am telling. Okay, nothing else. I am not showing any derivation or anything like that. Just a way to remember. What did I say? D dot ds is equals to rho v. If I am asking you about ds, that means you will think of normal. Normal d dot ds. So I need to think about d now. So for normal component, I have the relation with d. That is d2n minus d1n. How will you remember? d2n minus d1n dot a12. d2n minus d1n dot a12. d2n minus d1n dot a12 is equals to rho s, whatever the charge that is present here, whatever the charge density that is present here. And E dot dl, so that will be associated with tangential. E dot dl, E dot dl will be like one is associated with normal, so other one will be associated with tangential. So that will be E2t is equals to E1t. So since it is equals to 0, so there will be very simple relation. So this is known as our boundary condition. Okay. Now if rho s was 0, let's just say there was no charge here. If there was no charge here, then what would have happened? This rho s would become 0. Then what would have happened? That d2n will be equals to d1n. So if rho s was 0, then E1t would be equals to E2t and d1n will be equals to d2n. Is that clear to you? Now one more question is asked, that is the relation between tan theta 2 by tan theta 1. Basically they will give you this value and they will ask you the value of theta 1. So tan theta 2 ratio tan theta 1, what that would be? And remember what is theta? Theta is the angle made with perpendicular. Theta is the angle made with perpendicular, not with the surface. Not with the surface. It is the angle made with the perpendicular component of the boundary. Okay, so theta is the angle made with perpendicular, not this angle. In the examination, they can give you the diagram and they can mention this angle, and they can ask this particular angle. So for that, things will be different. I know the relation between these two angles. So what will be that relation? So let's check that out. So what will be your tan theta 2? What do you think? What will be my tan theta 2? Or first write down tan theta 1. First write down tan theta 1. So can I write tan theta 1? So that will be this divided by this, right? If I make another triangle here, this is your theta 1. So what will be this? This will be your tangential component of E or D, anything you can write. Anything you can write. And this will be your normal component. What I am talking about? I am talking about this direction. And what about this? This will be your normal component of E or D. Theta. This is your tan theta. So what will be this particular value? That will be tangential component, and this particular value will be normal component. So this is what I have written. So what will be my tan theta 1? Tangential by normal. What is tan theta? Perpendicular divided by base. Perpendicular divided by base, right? So what will be tan theta 1? That will be E1t divided by E1n, or you can write D1t divided by D1n. Anything you can write. Okay. What I can write? E1t divided by E1n, or it is equals to D1t divided by D1n, right? And what about tan theta 2? Same goes for this one as well. Tan theta 2, you can see like tan theta 2 will be this magnitude divided by this magnitude. So what will be this magnitude? So this magnitude will be equals to the tangential component only. Basically this is the vector which is in this direction. I can shift this vector here. So this will be equals to the tangential component only. So E2t divided by E2t divided by E2n. E2t divided by E2n, or you can say D2t divided by D2n. Now I need to find tan theta 2 divided by tan theta 1. So that will be any one I can pick, but I will pick the same one. If I am picking EE, then I will pick EE only. If I am picking DD, then I will pick DD only. So let's pick D. So tan theta 2 is D2 T divided by D2N into divided by tan theta 1 is there. So I just need to multiply with the reciprocal, right? So D1N divided by D1T. So these two are equal. This I am deriving for the condition if rho s is 0. Okay, if rho s is 0, for that only I am deriving. So if rho s is 0, so these two are equal. If these two are equal, then this and this is getting cancelled. Can I write it down as epsilon 2 d2t? What is d? D is equals to epsilon e. So can I write it down as epsilon 2, or I can write down epsilon r2, epsilon naught, epsilon r2 e2t divided by epsilon naught epsilon r1 e1t, and these two are equal. This is getting cancelled and this is getting cancelled. So tan theta 2 divided by tan theta 1, what that is coming as epsilon r2 divided by epsilon r1. This is the answer. So basically, relative permittivity of medium 2 divided by relative permittivity of medium 1, that is the relation between tan theta 2 divided by tan theta 1. Very easily you will be able to remember, right? If rho s is 0, then this is the formula. How did we derive it? Simply we wrote down the expression and then we derived this expression. Very easy, you will be able to remember very easily. But just remember what is theta. Theta is the angle made with perpendicular. Perpendicular of a boundary. Okay, perpendicular of boundary. Yes, let's solve this question. I just wrote it down in a good manner. Okay, angle made with the perpendicular of boundary. So let's solve this question now. Two dielectric media are separated by y equals to 0. So this is the plane equation. Epsilon 1 is given as 2 epsilon naught, epsilon 2 is given as 3 epsilon naught. Electric field expression in one of the medium is given. Okay, E1 is written, so in medium 1 the expression is given. You need to find the D1 for medium 1 and E2 and D2 for medium 2. Rho s is mentioned? No. If rho s is not mentioned, you need to take by default equals to 0. If rho s is not mentioned, I am taking it equals to 0. Why I am taking equals to 0? Because it is not mentioned. So in 9 out of 10 cases, it will never be mentioned. Okay, so by default you need to take as 0. And when we study the reflection of EM wave, which is our next topic, so in that as well we will take rho s equals to 0. Okay, so in our case it will always be 0, but there could be some numerical where they can give this particular value. So for that we need to consider it. But in this particular question it is equals to 0. So if that is equals to 0, then I know my boundary condition. So this is very important for me. If rho s is equals to 0, then these boundary condition I need to keep in mind. These boundary condition I need to remember, which is this: E1t is equals to E2t and D1n is equals to D2n. If you write it down for 2 to 3 times, you will be able to remember it. And since we are going to solve a lot of numerical, eventually you are going to remember it only. Now let's make the diagram first. So this is our y equals to 0 plane. This is our y equals to 0 plane. So at one side you will be having your electric field, which is this. This will be my electric field, which is having 4 ax cap plus 5 ay cap plus 6 az cap. 4 ax cap plus 5 ay cap plus 6 az cap. What will be its perpendicular? What will be its perpendicular? It could be plus minus ay. Look, I don't know whether it is y less than 0 or y greater than 0. I don't know that because they did not mention that E1 is traveling in y less than 0 or y greater than 0. I don't know that. Is that clear to you? E1 could be traveling in y greater than 0. E2 could be traveling in y less than 0, or it could be otherwise as well. So I don't know the region. So I cannot say whether it is plus ay or minus ay, but I know one thing, that it will be plus minus ay. Because what is the perpendicular component of y equals to 0? You can y minus 0, then you just take the gradient. So what you will get? Ay cap. That is very simple. I know the perpendicular component will be plus minus ay. So this is my electric field, that is 4 ax cap plus 5 ay cap plus 6 az cap. So the perpendicular component, what I can write, E1n, perpendicular component will be 5 ay cap and tangential component would be 4ax cap plus 6az cap, right? And what will this was my E1. What would be my D1? D is equals to epsilon E. What is epsilon? Epsilon is D1 will be equals to epsilon 1 E1. What is my epsilon 1? 2 epsilon naught. So 2 epsilon naught, and this is E1. So 4ax cap plus 5ay cap plus 6az cap. So what will be the normal component? Normal component will be the y1, so that would be tan epsilon naught ay cap. And what will be the tangential component? Tangential component will be 8 epsilon naught ax cap plus 12 epsilon naught az cap, right? Is that clear to you? Fine. What do I know by boundary condition? That E1t will be equals to E2t. So what will be my E2t? Tangential component of the electric field in medium 2. This is my medium 1. This is my medium 2. So in medium 2, my tangential component will be 4ax cap plus 6az cap. So tangential component I have found. And in medium 2, for the second medium, my D2n will be equals to what? D1n. So what is my D1n? D1n is equals to tan epsilon naught ay cap. Tan epsilon naught ay cap. So this will be my D2n. If I need to find E2n, then what that would be? That would be epsilon 2 E2n, right? D2n will be equals to epsilon 2 E2n. That would be tan epsilon naught ay cap. Basically, this is just the normal component I have found. And if I need to find electric field intensity from electric flux density, then I just need to apply by epsilon, right? But epsilon of second medium now, right? This is your electric flux density in the second medium. Now, if I need to find electric field intensity in the second medium, then I need to divide by epsilon of second medium. What is the epsilon of second medium? 3 epsilon naught. So epsilon of second medium is 3 epsilon naught. So that will be 10 by 3 ay cap. So this is my normal component of electric field in second medium, and this is my tangential component of electric field in second medium. So what will be my electric field in the second medium? That will be tangential component and the normal component. So that would be equals to 4ax cap plus this component in y direction I am writing plus this component 6az cap. This is your E2. Okay. And what about D2? D2 will simply be epsilon 2 times of E2. What is my epsilon 2? 3 epsilon naught. So just multiply with 3 epsilon naught. 4ax cap plus tan epsilon naught ay cap, which we got here as well, plus 18 epsilon naught az cap. This will be my D2. Okay, there you go. This is our first question. These kind of very basic questions can be asked from boundary condition. Just what you need to do, you need to equate tangential and normal you need to equate tangential component of electric field intensity and normal component of electric flux density. Is that clear to you? Tangential component of electric field intensity and normal component of electric flux density if your rho s is equals to 0. Okay, so this was the first question, which was very easy. Try solving this one on your own. Have you seen this equation anywhere? Have you seen this field anywhere? You have seen it, right? E1 can be written as its tangential component along this plane and its normal component along this plane. What was that? This was equals to this, right? This was the tangential component and this was the normal component. So shall we copy it here? Yes, we should copy it. So this we have already seen. Like this vector field we already saw, this vector field, and this was the plane only. So that's why I told this particular concept, that first you need to know the tangential component, you need to know the normal component as well, And if you can write down the tangential and normal component, then you can equate. So for now I am copying it here. Okay, I did not even leave the space, man. For now I am copying it here. .86 ax cap, 3.86 ax cap plus 5.79, 7.72, 5.79 plus 7.72 plus 1.14, 0.21. Okay, from here only I can write 1.14 ax cap plus 0.21 ay cap minus 0.72 az cap. Okay, so let's remove it off. So what do I know? Since again rho s is 0, so one thing I know is that I can find d1 now. So just it would be 2 epsilon naught into E1. So I am not writing down the complete expression, you just know that 2 epsilon naught will be multiplied with everything. Okay, or you can simply multiply 2 epsilon naught with this particular component, that is tan epsilon naught ax cap plus 12 epsilon naught ay cap plus 14 epsilon naught az cap. So this will be your E1 d1. Let's try finding d1 e2. E2 I need to find. So one thing I know is that E2t will be equals to E1t. So my E2t tangential component, that will be this. So my E2t is equals to 3.86 ax cap plus 5.79 ay cap plus 7.72 az cap. This is my E2t. What else do I know? What else do I know? I know that my D2n will be equals to D1n. Can I write it down in this manner? That my epsilon 2 E2n, epsilon 2 E2n is equals to epsilon 1 E1n. Can I write it down in this manner? D2 is equals to epsilon E, D1 is equals to epsilon E, epsilon 1 E1, epsilon 2 E2. What is my epsilon 2? Epsilon 2 is epsilon naught and epsilon 1 is 2 epsilon naught. This is your epsilon naught. This is your E2n and this is my 2 epsilon naught E1n. So my E2n would be twice of E1n. So my E2n would be what? Twice of this, 2 times of this. So what is 2 times of this? 2.28 plus 0.42 and minus 1.44, right? 2 times, that will be 1.44 az cap. So this is my E2n. Okay, this is my E2n. This was your E2n, this was your E2t. So can you write down your complete E2 now? Yes. If you go step by step, these questions are very easy. These questions are just based on mathematics. But if you go step by step, 3.86, 5.79. Otherwise, this would have become very difficult. In the examination, these type of questions are very difficult to solve actually. Just I need to add that up. So this will be my E2. 3.86 plus 2.28. 3.86 plus 2.28. So 6.14. 6.14 AX cap plus 5.79. 5.79 plus 0.42. 6.21 plus 7.72 minus 1.1, 7.72 minus 1.44, 6.28 AZ cap. This is the answer of your E2. And if I need to find D2, what that would be? Epsilon 2 E2. And epsilon 2 is simply equals to epsilon naught only. That will be epsilon naught E2. These are my answers. Okay. Very easily we are able to solve it. So just break it down in perpendicular and normal component. Sorry, perpendicular and tangential component. Tangential component of electric field are equal, tangential component of electric field are equal, but normal component of your electric flux density are equal. But electric flux density I haven't written here, right? Although I have written electric flux density, but why should I break it down into normal and perpendicular? Why should I do this calculation? Because I know that d1n can be written as epsilon 2 e2n, that would be equals to epsilon 1 e1n. So from there, epsilon naught to epsilon naught, twice of e1n, twice of e1n, e1n I already know, so twice of that, this will be 1.44, then just add them up. Tangential component you know, normal component you know, so from there you can write down your electric field, and from there you can write down your D2. Is that clear to you? Okay, let's solve next question. So now you are having some surface charge. Medium 2 is dielectric, medium 1 is conducting. No, it should be otherwise, right? Because wave is coming. E2T, D2. Okay, and this is correct. So medium 2 is dielectric, medium 1 is conducting, and this is your conducting surface only. Basically what is the scene is that this is a conductor and this is some dielectric medium, it could be air. You have just one conductor and then there is air around it. This is a conductor, there is air around it. So you can say this is your conducting surface which is acting as a boundary. Inside this there is conductor. Then this is the surface which is acting as a boundary. So this is also a conducting surface, and on this conducting surface you are having some rho s. Is that clear to you? What did I say? This is the other medium, this is a sphere. So a sphere is there, a conducting surface is there inside air. In the air there is a conducting surface. So inside this particular sphere there is some conductor, and this is the surface which is acting as a boundary, and this surface is also conducting surface. Is that clear to you? So all this is conductor, all this is conductor, and then this is dielectric. It could be air as well, we do not care about that. Okay, so these things you need to prove. E to T is equals to 0. Can you prove it? Yes. How you can prove it? The tangential component on conducting surface is 0. What do I know? Like on conducting surface there will be only normal component, right? This is my conducting surface, this is my conducting surface, conducting surface, right? This is your medium 1, this is your medium 2. So here your E1T will be equals to 0 because inside there is no electric field. Even on the surface there will be no electric field. Even on the surface there will be no tangential electric field. Like this will be also 0. Say yes or no? This will be also 0. Here the normal component will also be 0. This I can call D1n, or you can write down E1n. All will be 0 because inside there is nothing present. Here also you can call it E2, no sorry, D1t. D1t is also 0. Basically there is no electric field, nothing like that. So what is my boundary condition? That my E2t will be equals to E1t, and E1t is 0 only. There is no tangential component. So that's it. There you go. First thing is proved. What is the second one? What is the second boundary condition do I know? That my D2n minus D1n dot A12 is equals to rho s. A12 that is equals to rho s. What is my D1n? 0. D1n is 0. So D2n dot A12 is equals to rho s. Okay. Now tell me one thing. This is your rho s, right? On the surface of this conductor, you are having some rho s. Where will be your D2n? D2n will be this. This is your D2n, right? Electric flux density in the second medium, that is your D2n. Now this D2n dot A12, can you let me know what is the angle between D2n and A12? What is the angle between D2n and A12? This is the second thing which we need to prove, right? Second thing has been proved. What is the angle between D2n and A12? It could be 180, right? Or it could be 0 degree. Like if my A12 is this, A12 is this. So it is not 180, it is 0 degree only. A12. This is my A12. Perpendicular vector from medium 1 to medium 2. And this is your D2n. Perpendicular vector in medium 2. So what is the angle between them? 0 degree. So angle between D2n and A12 is equals to 0 degree. If it is 0 degree, then what will be the value of this? A12, this is a unit vector. So magnitude of D2n dot magnitude of this guy, that is 1, magnitude of A12, that is 1, angle between them cos 0. So that would be equals to magnitude of D2n only. So magnitude of D2n is equals to what? Rho s. That's it. That's it. Third thing is proved. Is that clear to you? And what do we write down the boundary condition? D2n minus D1n. D2n minus D1n dot A12 is equals to rho s. So there also we can write down D2n minus D1n magnitude is equals to rho s. This is correct. Why is that correct? Because D2n minus D2n minus D1n will be in the same direction of A12. Is that clear to you? All are normal component, no? D1n, D2n, all are normal component, and dot A12 normal component. Both are having angle 0. If they are having angle 0, what is the magnitude of A dot B cap? Magnitude of A dot B cap, that is equals to magnitude of A dot magnitude of B, the magnitude of A dot magnitude of B cap into cos of angle between them, that is cos 0. So that will be equals to magnitude of A. Same goes here. Okay. So this is also true, which I should have taught in the boundary condition only, but since this question has come up, so this you can write down. And in case of conductor, this guy will be 0. In case of conductor, this guy will be 0. So if this guy is 0, then what will happen? This guy will be 0. So what will happen? The magnitude of D2n will be equal to rho s. Magnitude of D2n will be equal to rho s. Is that clear to you? So that completes our one of the what do we say? We proved one thing, that our electric field will always be perpendicular to the conducting surface, right? Our electric field will be always perpendicular to the conducting surface. Yes, only perpendicular component is coming. Normal component is, sorry, tangential component is 0. Our electric field is always perpendicular to the conducting surface. So only perpendicular component is coming. This tangential component is coming out to be 0. E2t is coming out to be 0. This component is 0. 0. So we are not even showing it. So outside the conductor, always normal component you will find. Normal, 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 normal. No tangential component would be there. So this has proved one of the phenomena that we proved initially without even using boundary condition. Using the boundary condition, we have proved it now. Is that clear to you? And very important result we got here, which is our third answer, this one. Okay, no need to mug it up, but we have proved it. So in the examination also you will be able to prove it with simple this explanation, right? Let's move to the next question. So this is a charge free boundary, E1, E2, making an angle of theta 1 with the perpendicular, making an angle of theta 2 with the perpendicular. Theta 1 is mentioned, you need to find theta 2. Epsilon r is mentioned, epsilon r is mentioned here. So what do you know? That tan theta 2 divided by tan theta 1 is equals to what? Fit it out, yeah. tan theta 2 divided by tan theta 1. What that would be? Tan theta 2. So epsilon of this one, root 3 epsilon naught. Tan theta 1, so epsilon of this one divided by 3 epsilon naught. So tan theta 2 divided by tan theta 1, tan 60 is equals to root 3 divided by 3, 1 by root 3. So tan theta 2 divided by 1 by under root 3, that would be under root 3. So what is the value of theta 2? 45 degree. Very simple question. These kind of questions can come up. Sometimes these kind of questions can also come up. But always remember this theta 2 is the angle made with the perpendicular. If I had asked you this angle, then what would have been your alpha 2? Alpha 2 would have been 90 minus 45 degree. That would have been 45 degree. Right? And in the examination, if I had mentioned this angle, then let's just say this angle I would have mentioned, that is 30 degree. So in the examination, this information was not even given. Okay, this was your question in the examination, and this theta 1 was also not mentioned. Then how you would have solved it? Find theta 2 and find alpha 2. If this was the question and this was made 30 degree, then what you would have done? You would have called this as theta 1 and you would have said that it is 60 degree. Then tan theta 1 divided by tan theta 2, or tan theta 2 divided by tan theta 1 will be equals to epsilon of this second medium, epsilon of first medium. You wrote this, then you find out this value. Very easy, right? Okay, yeah. So let's move to the next one. The displacement flux density D is given at a point on a surface of perfect conductor. Surface of perfect conductor D is given. On the surface, this is your conductor, and on the surface D is given. So can you let me know where it will be? Perpendicularly only, no? This is the surface. I don't know where this surface is. I don't know where this surface is, but I know that always perpendicular only it will exist. So this will be certainly perpendicular. D2 and if someone asks you if someone is asking you the equation of this surface, so equation of this surface I don't know, but one thing I know that any point which is lying on this surface, so all these vector will be perpendicular to this. Forget about this point, okay? I am just making it complex, so forget about the previous point which I said. The only thing you need to know that on a surface of perfect conductor, if D2 is existing, that means that has to be perpendicular only, right? So this D2 is equals to D2n. So what I mean to say is that D2n is equals to D2. That is 2ax cap minus under root 3 az cap. You need to find, and it is pointing away from the surface. This electric field, or you can say electric flux density, is pointing away from the surface. What does that mean? That this charge would have been positive. Pointing away, that means positive charge. So my charge density will be positive. Is that clear to you? My charge density, what do you need to find? Rho s. So certainly rho s will be positive, that I know. My rho s will be positive. Okay. Now rho s will be positive. Now what will be my rho s? What did you understand? That your d2n, mod of d2n is equals to rho s. And how this formula came? That d2n minus d1n is equals to rho s. And inside the conductor, what is this? d1n is 0. Inside the conductor, d1n is 0. So mod of d2n is equals to rho s. So what will be your rho s? Mod of this guy. What is the mod of this guy? 2 into under root 1 square plus under root 3 square. So 1 plus 3. That would be 4. So rho s is plus 4 coulomb per meter square. Is that clear to you? This is the answer. How did I find it? Did you understand how did I find it? Pointing away, positive. D2 is existing. So here I am not going to break down in normal and tangential, because I know that on a surface, if D2 is existing, that has to be normal only. So that is normal only. So and the magnitude of that is equals to rho s, which we have previously proved, because d1n inside will be 0. So that will be equals to rho s. Is that clear? Okay. So are we left with any other? No. So now we are going to start a magnetic boundary condition. That is also very easy. In the same manner we are going to solve problem as well. So magnetic boundary condition we will see, but let's take a break. After the break we will start it. So you can also drink some water and you can try deriving the expression. Like, what do you know? I am not asking you to derive the expression, but try thinking about it, that what component will be associated with what. Like normal component will be associated with B or H, and tangential component will be associated with H or B, right? So what do you think? What will happen? The normal component will be associated with B, and tangential component will be associated with H, right? And since it is equals to 0, then it will come very easily. How it will come? B1n is equals to B2n, right? You can break it down. This will be normal, this will be your tangential, this will be normal, this will be normal, and this will be tangential. So I am not writing down B2H, B2n, B1n. You would know, right? This will be your, so this will be your H2T, and this will be your B2n. This is your H1T, and this is your B1n. Okay. So normal component will be equal. How will I remember it? In a longer run, eventually I will be remembering it. But for a shorter time, if I need to remember, so B dot ds is equals to 0. ds is associated with normal. That means B is associated with normal. And if it is equals to 0, that means very simple expression will come. That is, both will be normally equal. Is that clear? So in case of magnetic field across the boundary, magnetic flux density are continuous. Did you understand this statement? In case of a magnetic field across the boundary, magnetic flux density are equal, or you should say magnetic flux density are continuous. So B1n is equals to B2n. Crystal clear? What about this H relation? So that relation is complex. How do you find that? What you need to do? Here one more thing will be there. What is that? Medium 1 to 2, A12, medium 1 to 2, A12, right? So tell me one thing. One thing you know, that it will be associated with tangential component, right? This will be associated with tangential component. Are you getting this point? H will be associated with tangential component because normal component we have already written. Now we need to write tangential component. So how will I write it down? This is K, this is your A12, and this is your H2T minus H1T. So these are three words. This word is having only one letter, this word is having 3 letters, and this word is having 6 letters, right? K is having only one letter, this is having 3 letters, this is having 6 letters. So in that manner you will write down that K is having least letter. So first I will write down K, then I will write down A12, and then I will write down H2T minus H1T. In the previous one, what did I write? D2n minus D1n, D2n minus D1n. So similarly, here I will write H2T minus H1T. So I will start with K, which is having least letter. It is having only one letter, K. Here A12, 3, H2T, H1T, 6. So K, A12, H2T, H1T. Then cyclic. The cyclic order I will do. So if I do this thing X, Y, Z, what do I say? That X cross Y will give me Z, Y cross Z will give me X, Z cross X will give me Y, right? X cross Y gives me Z, Y cross Z gives me X, and Z cross X gives me Y. So in the same manner here also I will tell. What do I say? If I need this value, then how will I get it? K cross A12 cap. So H2T minus H1T is equals to K cross A12. A lot of people get confused in the sign, but this is the best way to remember, that you will have H1T, you will have H2T. So H1T relation H2T you need to write. In electric boundary condition, what did we write? D2n minus D1n. So second medium first. So here also I will write H2T minus H1T. What I'm gonna write H2T minus H1T. I will have K. that is not surface current, this is surface current density. Okay, do you remember what is surface current density? I took a small paper which was having good width but the length was very small. Then I said that some current is passing. So some current will be passing from here. Some current will be passing through the surface. This is my surface. This is my surface. So current will be passing like this. Current will be passing like this. It will be cutting this particular line. So it feels like that the current is cutting this line. So what was the unit of surface current density? Although the name is surface current density, but the unit was ampere per meter. So how much current is crossed by this line? From this line, how much current is going? So that was known as surface current density. So this is our surface current density. So I am having three letters K, A12, H2T minus H1T. So in that manner I will write down, then cyclic I will do. Cyclic rotation I will do. Okay. So H2T minus H1T is equals to K cross A12. If I need to find K, then what I will write down? If I need to find K. So how can I get K? A12 cross H2T minus H1T. Say yes or no. If I need to find K, if I need to find surface current density, then how will I get? This is how I can get K. And if I need to find A12, then how will I find A12? A12 will be equals to H2T minus H1T into K. So if I need to find A12, A12 is the perpendicular, A12 is the unit vector from medium 1 to medium 2 in perpendicular direction, 1 to 2. Okay. So if I need to find A12, how will I find it? This cross this will give me A12. So H2T minus H1T cross K. H2T minus H1T cross K. This will give me A12 cap. Is that clear to you? Okay. So this is my magnetic boundary condition. Same magnetic field was coming, magnetic field was going. Two components, tangential and normal, tangential and normal. Two components across this boundary. Now this boundary is having some surface current as well. It can have some surface current, right? This is your boundary. This is having some surface current density. Okay, surface current density, that is K, that is ampere by meter. So normal component will be equals to 0. How I am writing it down? B dot ds. So in a longer run I will be able to remember this, but in a short term memory, if I want to remember, then how will I remember that B dot ds is equals to 0? Okay, B dot ds 0, that means very simple formula will come, and ds is associated with normal component, so B1n is equals to B2n, and then H dot dl, so that will be associated with tangential component. Since it is not equals to 0, it is equals to some I enclosed, so formula will be complex. So that is the formula. How will you remember this formula? This is the way to remember this formula. K, least letter, A12, H2T minus H1T. So if you remember by this particular phenomena, if you remember by this particular analogy, then you will be able to remember it for a longer run. K, A12, H2T minus H1T. So K cross A12 is equals to H2T minus H1T. That's it. Okay. Now if K is 0, if this is 0, then what will happen? B1n is equals to B2n and H2T is equals to H1T. If K is 0, then B1n is equals to B2n, H2T is equals to H1T. If I need to find this value, tan theta 2 divided by tan theta 1, what that would be equals to? Considering that my K is equals to 0. K is equals to 0 ampere per meter. So tan theta 2 divided by tan theta 1. So I will take a break. Now I will take a break. Here I have explained the boundary condition. So now I will take a break. You derive it on your own and let me know what is the formula you are getting. Okay. So after that we will derive it. Yeah. So let's start. So let's write down tan theta 2. What will be my tan theta 2? Tan theta 2 will be this by this, right? You can see that triangle here, right angle triangle. So that would be, in terms of B I am writing. So I will write down B2T divided by B1N. That will be B2T divided by B2N, not B1N, sorry, B2T divided by B2N. Tangential, this I have just shifted here. So B2T divided by B1N. This is my B1N. Sorry, B2N. Sorry, B2N. B2T divided by B2N. B2T divided by B2N. What will be my tan theta 1? Tan theta 1 will be tan theta 1. This will be B1T divided by B1N. B1T divided by B1N. Okay. So if I do tan theta 2 divided by tan theta 1, and what will happen? B2T divided by B2N, then simply the reciprocal, B1N divided by B1T. So this and this getting cancelled, and since I am deriving for k equals to 0, then what will happen? B2 can be written as mu naught mu R2 H2T. Say yes or no? And B1T can be written as mu naught mu R1 H1T. Is that clear to you? Say yes or no? Right? This is how I can write it down. Mu naught mu R H2T, mu naught mu R1 H1T. Right? B equals to mu H. This and this get cancelled. This and this get cancelled because H2T is equals to H1T. So what you are getting? Tan theta 2 divided by tan theta 1, that is equals to mu R2 divided by mu R1. So this is what we are getting. Okay, this is the ratio of tan theta 2 divided by tan theta 1. In the electric field case, what it was? ER2 epsilon R2 divided by epsilon R1. Here it is mu R2 divided by mu R1. Very easy to remember. Tan theta 2 is equals to tan theta 2 divided by tan theta 1 is equals to mu R of this medium divided by mu R of that medium. Okay, that's all this question. What we need to find? Medium 1 is at z less than 0. So let's draw the diagram. So always draw the diagram first. Medium 2 is z less than 0, so this would have been z equals to 0. So medium 1, this is your medium 1, that is z less than 0 is having mu r of 6. Okay, and this is your medium 2, that is z greater than 0, it is having mu r of 4. This is z equals to 0 interface. Surface current density, that is 1 by mu naught ay cap. So where it would be? 1 by mu naught ay cap. So this is z equals to 0. That means if I am saying this is z equals to 0 plane, so this is my x, this is my y, and this is my z. No, this cannot be z. So x, y, x cross y will give me z. Yeah, okay, fine. So somewhere here the current would be 1 by mu naught ay cap. So I don't need to show the direction, but you just need to know that surface current density is there on this particular surface. This is your boundary. So on this boundary, on this surface, there is some surface current density. On this surface, there is some surface current density. This is what they are saying. Okay. B2 expression is given. B2 expression, not B1 expression. B2 expression is given. You need to find the expression of H1. B2 expression is given. You need to find the expression of H1. Very good question. Okay. So B2 expression is given. 5ax plus 8az. 5ax cap plus 8az cap. And z equals to 0 plane is that. Z equals to 0 plane. So what will be my, first tell me what will be my A12? Medium 1 to medium 2. Medium 1 to medium 2. Medium 1 to medium 2. This will be my A12. What is that? A12. You are going from z less than 0 to z greater than 0. This is your z equals to 0 plane. This is your z equals to 0 plane. This is your z equals to 0 plane. This is your medium 1 and this is your medium 2. Is that clear to you? You are going from here to here. And this was your surface current density on this particular plane. Shall I make it more clear? So this is your z equals to 0 plane. This is z greater than 0 and this is z less than 0. And where this is my y coordinate, so this is my surface current density. Okay, in this direction I am having surface current density. Okay, now A12, medium 1 to medium 2. So medium 1 to medium 2, perpendicular unit vector. So this will be your perpendicular unit vector, which is Ez cap. Let's write it down more clear. medium 1, medium 2. So A12 is AZ cap, right? Okay. And so what will be my perpendicular component? Perpendicular component will be 8 AZ cap. And what will be my tangential component? This will be my tangential component, right? This is your perpendicular component. And this is your B2N, I can write. This is my perpendicular component and this is my tangential component. अरे यार क्या कर रहा हूँ मैं? So what do I know? That B2N is equals to B1N. This is always true. So my B1N is equals to 8 AZ cap, right? Normal component will be equal. What is the normal component? AZ cap. Normal component is AZ cap. So what is my normal component? 8 AZ cap. Normal component is 8 AZ cap. So B1N will be equals to 8 AZ cap and B is equals to mu H. So mu1 H1N is equals to 8 AZ cap. So what will be my H1N? 8 by mu1. What is my mu1? 8 by mu1. 6 mu naught. 8 by 6 mu naught. So what you are getting? 4 by 3 mu naught AZ cap. This is your H1N. Is that clear to you? Now I need to find the tangential component. For tangential component, what do I need to do? K A12 H2T minus H1T. So H2T minus H1T is equals to K cross A12. Do I know B2T? Yes. What is that? 5 AX cap. Can I write it down H2T? Because B is equals to mu H. This is equals to mu2 H2T. So from here what it would be? 5 by mu2. What is mu2? Mu2 is 4 mu naught. Mu2 is 4 mu naught, right? This is your mu2. So mu r is 4 here. So for medium to mu r is 4. So this will be 4 mu naught. So this is what you are getting. That is your H2T. So this is my H2T. But I need to find H1T. H1N I have. H2T I have got. I need to find H1T. So what is my H2T? H2T is 5 by 4 mu naught AX cap minus H1T I need to find. What is my K? 1 by mu naught AY cap. So once you solve these problems with good amount of patience and in a manner, like don't run behind it like quickly I need to solve. No. In a certain manner, if you solve it with good amount of patience, you will never get it wrong. So always have the patience. Gate is never the examination of your speed. What is your A12 AZ cap? Gate is always the examination of accuracy. You will never feel like that the time was less. No, it never happens. Believe me, it will never happen that time was less. But you will get answer wrong if you solve it quickly. You will be able to solve the problems of analog quickly. Network you can solve quickly. Digital you can solve quickly. But you should solve EMFT with good amount of patience. You should solve EDC with good amount of patience. You should solve communication with good amount of patience. So these subjects requires patience. If you solve it patiently, like in this manner, like in a certain manner, if you solve, you will never get it wrong. Okay. So 5 by 4 mu naught. But what happens is that like people are always in hurry that I will solve it quickly. In that manner, you will do some calculation mistake and everything will be messed up. So 1 by mu naught y cross z will give me x. So what is my H1T? H1T is 5 by 4 mu naught AX cap minus 1 by mu naught AX cap. So 5 by 4 minus 1, what that would be? 1 by 4 mu naught AX cap. This is my H1T, 1 by 4 mu naught AX cap. Okay. So what I am getting now? what is my H vector? So H1t plus H1n, H1t plus H1n. So 1 by 4 mu naught Ax cap plus 4 by 3 mu naught Az cap. This is your answer. This is your answer. Okay. 1 by 4 mu naught plus 4 by 3 mu naught Az cap. This is how we solve it. Very easy question. If they are going to ask anything, this is the maximum they can go. Only these kind of questions they will ask. So B2 they will give, or they could have given B1, they could have asked you H2, but here I have given B2. I have given the reflected wave. I have given the wave in the second medium. So the second medium wave I have given, I have asked the wave in the first medium. I should not say wave, this is field, this is not wave. Wave is the combination of E and H. This is field. So I should not call it wave, this is magnetic field. So magnetic field expression, magnetic flux density expression in the second medium is given. I was asked to find magnetic field intensity expression in the first medium. So very easily, if I go with good amount of patience, I was able to find it very quickly. B2, I wrote it down. Then B2n, B1n is equal. From there I got the H1n. Then I know that B2t I have. Then I can write down the H2t value. And one thing I know that if I go in the cyclic manner, then K A12 and H2t minus H1t. I need H2t minus H1t. So K cross A12. So H2t I know 5 by 4 mu naught Ax cap. Then from there H1t I got H1t plus H1n is equals to H. Right? What is my H? H is H1t plus H1n. So from there I got this answer. Is that clear to you? So that's it about our magnetic boundary condition. There is one more point, which is boundary condition for current density. So this is our current density, that is J1 in medium 1, and this is our current density, that is J2 in medium 2. I have made this angle larger. There is no meaning of that, right? You will say that, sir, in previous cases you made this angle lower and here you are making this larger. No, there is nothing conclusive from here. This is just I made it. I could have made it like this as well. Okay, I just made it, so don't get confused that, sir, why this is larger. Nothing like that. There is no conclusion from here. This is just the diagram. So in medium 1, which is having its own sigma mu epsilon, and medium 2 is having its own sigma mu and epsilon. So this is having current density J1, this is having current density J2. So what kind of boundary condition we can apply? So it will also have its own tangential and it will also have its own normal and tangential component. Normal and tangential component. So I will just ask you to remember few simple things. I hope you will be remembering those things. Okay. So this was my J1t. Sorry, J1. This was my J2. So this would be my J1t. And this would be my J1n, and this would be my J2n, and this would be my J2t. Tangential component, normal component. So first let's study KCL. Have you studied KCL in network analysis? That if I1 current is coming, I2 current is coming, I3 current is coming here, then I4, I5 and I6. Basically I1 plus I2 plus I3. These are the incoming current will be equals to I4 plus I5 plus I6, right? So forget about I2, I3, all these things. Current is not a vector quantity, right? But current density is vector quantity. Current is not vector quantity, but current density is vector. So if I am saying that current is coming in this manner, can I say that current density is flowing in this direction? Like this is your J1 current density, this is your J2, J3, J4, J5, J6, and the direction are shown by the arrow. If I ask you the divergence at point P, dial dot J, divergence of current density at point P, what that would be? 0. Why is that so? Because the number of lines which are converging, is equal to the same which are diverging. Do you remember this thing? That these are the vector lines which are going out and these are the vector lines which is coming in. So whatever that is coming, that is flowing out. Divergence is equals to 0. And if all are flowing out, if this is the scene that all are flowing out, then it is positive, and if all are converging in, then it is negative. Do you remember this thing? In vector calculus we have studied it. So here whatever that is coming, that is flowing out. This is our KCL, right? What do you mean by KCL? The current at a node is equals to 0. The addition of current at a node is equals to 0. I1 plus I2 plus I3 minus I4 minus I5 minus I6 is equals to 0. So at the point, always the divergence will be equals to, at any node in the circuit, the divergence of current density will be equals to 0. Is that clear to you or not? Del dot J is equals to 0. Whatever the field lines are coming, the same are flowing out as well, right? So this is our KCL. This is what? This is our KCL, right? Now can I write it down in this manner? That my, sorry, J dot ds, what that would be equals to? J dot ds would be equals to del dot J dV, and del dot J is equals to 0. 0 dot dV. What you are getting? 0. So what did you get here? J dot ds is equals to 0. So this is also our KCL. So this is not a Maxwell equation. This is not a Maxwell equation. That's why we did not study it. But when we are studying boundary condition, that I need to teach it. So that's why I am telling it. This is your KCL. KCL is J dot ds equals to 0. So till this discussion, you just need to remember one thing, that is J dot ds is equals to 0. From here, can you write down one boundary condition? How will you write down? So J dot ds is equals to 0. ds, that means normal. Normal of what? Normal of J. So from here, what you can write down? That sir, J1n will be equals to J2n. Is that clear to you? So this is one of the boundary condition. This is our one of the boundary condition. What is the other thing you know? That sir, E dot dl is equals to 0. Right? Can E be written as J by sigma dot dl is equals to 0? Say yes or no? Sir, E dot dl is equals to 0. Can I write it down as J by sigma, because J is equals to sigma E? So this is what I write down. dl means tangential component. dl means tangential component. Tangential component of what? J by sigma. So that means J1t divided by sigma 1 will be equals to J2t divided by sigma 2. There you go. This is the second boundary condition. In the worst case, if you forget in the examination, then you can think in this manner. That's why I am teaching. This is not a proof. Okay. I am not showing any derivation, because derivation for this is completely not useful for your examination. That's why I did not show the derivation. If it was useful, then certainly I would have shown the derivation. I neither showed the derivation of electric field, electric boundary condition, neither I showed the derivation of magnetic boundary condition, neither I am showing the derivation of this. Here you just need to remember the results. Results are very important. And how will you remember the result? That also I am telling it. Why do we do the derivation? So that we remember the result in a good manner. If you directly remember result, and if you remember result by doing the derivation, you will remember the result more clearly once you do the derivation. But here, if I am not doing the derivation, then at least I am telling how to remember these results. So J dot ds is equals to 0. ds associated with normal. Associated with normal. Normal of what? Normal of J. So J1n is equals to J2n. dl associated with tangential. Tangential of what? Tangential of J by sigma. So J1t divided by sigma n is equals to J2t divided by sigma 2. There you go. No need of proof. No need of proof. Okay. So these are our boundary condition. These are your boundary condition. And tan theta 1 divided by tan theta 2 is equals to sigma 1 divided by sigma 2. This you can derive on your own. Okay. Very easily you can derive. But since we are writing theta 2 divided by theta 1, so here also I will write down theta 2 divided by theta 1. So that would be equals to sigma 2 divided by sigma 1. In case of electric field, what it was? Epsilon R2 divided by epsilon R1. In case of magnetic field, what it was? Mu R2 divided by mu R1. In case of flux density, what it is? Sigma 2 divided by sigma 1. Is that clear to you? Okay. So these are our boundary condition. Normal equal, tangential component equal, but divided by sigma 1. How will you remember? E dot dl, J by sigma, dl tangential, J by sigma. So J1t divided by sigma 1, J2t divided by sigma 2. And this is equal. Very rarely it can be asked. Okay. Till now, never they asked about the boundary condition of current density, but it is mentioned in this Cheng book. That's why we are studying it. Since these points are mentioned in the book, that's why we are studying it. So in one liner or in 1 mark of question, they can ask these kind of question in the statement. Okay. So these are our 3 results which you can remember. So let's write down the summary of our complete discussion. So let's write down the summary. So what is the summary? So what is our electric boundary condition? That E1t is equals to E2t. So I will write it down again so that you also do it. So you also write it down on your own. So what did we studied? That my E2t will be equals to E1t. What is the second thing we studied? D2n minus D1n from 1 to 2 will be equals to rho s. And if rho s is equals to 0, then D2n will be equals to D1n. So these are the 2 things we have studied. Is that clear to you? And what is my A12? Medium 1, medium 2, this is your boundary. So 1 to 2 perpendicular unit vector. 1 to 2 perpendicular unit vector is your A12. What about magnetic boundary condition? So what we studied? That B1n is equals to B2n. What about H? For H, we do not remember anything, but what I know, there will be 3 things. K, which is having the least letter, then A12, then in the last H2t minus H1t. Okay, these will be the 3 things. So H2t minus H1t is equals to K cross E12, and if K is equals to 0 ampere per meter, and this would be coulomb per meter square, and if that is 0, then H2t minus H2t will be equals to H1t. Okay, here one more important result from here. What did we get to know? That your D2n minus D1n magnitude is equals to rho s, right? So sometimes these things can also be asked, and from here anything can be asked. Like if they are asking K, so how will you write down? That K will be equals to A12 cross H2t minus H1t will be equals to K. Okay, so these are the things, and then in the end J1n is equals to J2n, J1n normal component, J dot ds is equals to 0. ds is associated with normal of what? J. So J1n is equals to J2n, and then about tangential component, J1t divided by sigma 1 is equals to J2t divided by sigma 2. E dot dl, J by sigma. So this is how we can remember these 2 results as well. So this is our complete summary. Only these things if you remember, you will be able to solve any problem. And what was our tan theta 2 divided by tan theta 1? What was our theta? This was the theta. Okay, what was the theta? First let's show the theta. So this is our boundary, this is our normal, and this is the field line. This is the field line. This angle is theta 1 and this angle will be theta 2. Okay, it would be electric field line, it would be current density, it would be magnetic field line. So what was the formula? ER2 divided by ER, epsilon R2 divided by epsilon R1, mu R2 divided by mu R1, and sigma 2 divided by sigma 1. There you go. These are the final formula. So this is the summary of everything that we have studied. Previously, in the first 30 minutes of the video, in first 30 minutes, what did we study? We studied about vector algebra, and then we studied about conductor. In the conductor, how the field goes. Then we move to the boundary condition. Then electric boundary condition, then we saw some numerical, then magnetic boundary condition, we saw one numerical only, then this current density. Okay. So yeah, that's it about this lecture. Now you do not need to solve PYQs of boundary condition. What I am saying, you do not need to solve PYQs of boundary condition. Why is that so? Because those PYQs will involve some concept of electrostats and magnostats. उनमें electrostats भी आएगा, magnostats भी आएगा, but that is not in our syllabus. So PYQs you don't need to solve, just revise this lecture, whatever that I have taught. Everything will be asked from this lecture only. I am talking about ECE student, not electrical student. Electrical students are taught boundary condition in much depth manner. Also they will have more numerical. That will involve the concept of electrostats and magnostat. But since we do not study electrostat and magnostat, only this much of concept can be asked in your examination. For ECE student I am asking. Okay. So ECE student do not need to solve the PYQs of boundary condition. PYQs of plane wave we are going to solve, like EM wave PYQs we are going to solve. All the concept of EM wave, transmission line, waveguide, antenna, all those PYQs we are going to solve. But we are not going to solve the PYQs of boundary condition. So your boundary condition is confined with respect to this particular video only. Whatever that you have studied in this video, that will be everything for you in case of boundary condition. Is that clear to you? Okay. So that's it about this video. In the next video, we are going to study about the reflection of EM wave, reflection and transmission. So now there will be one medium, here there will be some medium 1, here there will be some medium 2. So our EM wave will travel and it will incident normally. So first we will study about normal incident, then we will study about oblique incident. So our EM wave will incident normally, some part will be transmitted, some part will be reflected back. So that study we are going to do, that how much part will be transmitted, how much part will be reflected back. So there we need to apply boundary condition. That's why we have studied it. Also we studied it in depth manner because it is in the syllabus as well. Is that clear to you? Okay. Thank you very much. So let's meet in the next lecture.